Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, let's get started with this afternoon's session on EScience in Systems. Our first speaker is Fritz Wollenweber from
EUMETSAT.
Thank you.
EUMETSAT is the European meteorological satellite operator. And I wasn't able to switch off the screensaver. So I would like to acknowledge the contributions of my co-authors, Christian Marquardt and Jago Andres, who are both with EUMETSAT, and René Sandbergen and Maria Lorenzo, who are with ESOC, which is the ESA European Space Operations Center. Also, these both organizations are located in Darmstadt, Germany. So what I'm going to talk about is first I will briefly introduce the radio occultation and the GRAS instrument. I don't know whether you are familiar with radio occultation. Then the GRAS GSN requirements, the system architecture, the operations concept, and finally I will show some of the results we are getting. GRAS is basically it's a GPS receiver embarked on a METOP satellite. METOP is the polar orbiting satellite of EUMETSAT. It's a 4.5-ton satellite, the size of a truck, and it's besides GRAS, which is the top bubble here, pointing to one of the GRAS antennas, and besides GRAS, it has a number of other instruments which I will completely ignore today. This is the GRAS instrument, and here the two big panels you see are the main antennas that observe what we call radio occultations, and the small panel in the middle is a zenith antenna, which is used for, like a handheld GPS receiver to do positioning. You see also some of the electronics and onboard processing units. This diagram tries to explain a bit of the basics of radio occultation. This technique is not new. It has been used on a long time into the 60s, 70s to get properties of planetary atmospheres from Mars, Venus, and other planets. And we are using this on planet Earth. Here, basically, electronic waves are bent through the refractivity in the atmosphere. And the more the METOP satellites, which is flying in about 800 kilometer altitude, is hiding behind Earth with respect to a occulting GPS satellite, which is flying at 20,000 kilometers. The longer the path gets, and the more you get radiation that goes directly through the atmosphere. You can measure now the time or phase delay or path length extension that is caused then by the atmospheric propagation. And when you have a very good knowledge about the position of both the METOP and the GPS, their velocities and the clocks, the times on board of all these spacecraft, then you are able to derive properties of the atmosphere itself. On this slide, I'm showing a little bit on the underlying refractivity. Here you have three terms, basically. One is a tritterm, which is depending on pressure and temperature. Second one is a so-called wet term, which depends on vapor pressure and temperature squared. And the last term is called the electron term, which is depending on electron density, basically. This term obviously is most important in ionosphere. The wet term is most relevant in the lower part of the troposphere. And the dry term is basically effective throughout the sounding here. In the second bullet here, I try to characterize a bit the characteristics of the measurements we are taking here. This method is particularly interesting because it's a very stable measurement principle per se. So you don't need to have complicated calibration on board. It delivers a very high vertical resolution, at least in around the tropopause or the lower stratosphere, of about 800 meters in the vertical. One of the features is that it's horizontally integrating because you can have a very long path through the atmosphere, which means an integration length of about 200 to 400 kilometers. And when you use, and in addition, of course, depending on the relative spacecraft motions, this integration path is not constant. It's also changing with time. So you see different aspects of the atmosphere, and you have to understand the measurements principle and the measurement quality very good. But you end up with very accurate temperature soundings, and in a region higher troposphere, lower stratosphere, where you normally don't have so many very good quality observations. So these radio occultations find their applications for me primarily in climate monitoring, because here you look at climate changes which are, in absolute terms, relatively small, but they can have very strong impact. And currently, the measurement systems that are used are not very well distributed. You have a lot of measurements over the continents and the northern hemisphere, but a lot less over oceans and the southern hemisphere. And there, this measurement system comes in very nicely. Here I show the number of observations we get within 24 hours typically. Yeah? We have here about 1,300 occultations, which is a big improvement over the conventional observation system. And this is a latitude-longitude display, so it's also nicely, geographically distributed. This is a latitude local time display. And here you see that you get between 60 north and 60 south. You have cover only certain local times, namely 9:30 a.m. and p.m. That has to do with the orbit characteristics of MEDOP, which is a sun-synchronous satellite with an equator crossing at 9:30. And this is what you see here. So basically, we are always telling people that we need more instruments. Basically, you need a constellation of these instruments to get a full coverage also in time domain. But it's a start. This is a slide which I borrowed from a colleague from ECMWF, the European Center for Medium Range Weather Forecast, where she tried to analyze what impact this radio occultation technique makes on their analysis of the state of the atmosphere and the forecasts. And I don't want to go too much in the details of the parameters which are shown here, because the only thing I want to show here is that you see the major contribution is between 10 and 35, 30, 40 kilometers altitude. Yeah. So now I'm come to the GRAS support network, which is basically the real contents of the talk. And this GRAS support network was put in place because we have a need to get very precise orbits of both the GPS satellites and the MapReduce satellite. We need very precise clocks on all spacecraft. And if the clock stability hadn't turned out as stable as it turned out, we would have had different processing algorithms that would have applied several double, single differencing, double differencing, and then we would have needed, in addition, these ground data of the GPS ground stations to get also the clocks of the ground stations very accurately. The GRAS GSN high-level requirements are for 15 years, to support 15 years of operation, because we have a series of 3 spacecraft, each with a nominal life of 5 years. We ask for a system availability of better than 99% on a 24/7 operations. We ask, in order to be able to deliver our products to the end user within 2 hours 15 from observation, which is a requirement on us, we need to get this additional data within 60 minutes of observation in order to have enough margin to do the subsequent processing. We need precise orbits. The requirement was 1 meter, 3-dimensional accuracy. And we need precise clocks, and here we give 0.5 nanosecond for the clock stability. Another option, another point which was put in the requirements is that this support net can also support other missions and other satellites, and we actually exercised this option in support of the cosmic constellation, which is a cooperation between Taiwan and the US. And we deliver operationally now these GSN products also to the cosmic processing centers in Boulder and in Taiwan. We have put in place a dedicated receiver network, which is provided by 4 different network providers, which is ESOC, GFZ, which is a German geo research center, Fugro, which is a commercial company which is providing maritime services and uses GPS for this, and National Resources Canada, a government organization. In order to cover a gap in the South Pacific, ESO put a station on Tahiti, and Météo France, the National Weather Service of France, is providing the hosting this station and providing the support on site. We have in total about 46 sites, of which 25 we classify as prime sites. This is the minimum that we need to guarantee the quality of service which is required. Data is delivered in 15-minute batch files from all over the place. And we are currently looking at the possibility to go into a real-time mode, that we get data as it is received by the GPS ground stations. This is giving the global distribution of the prime sites, and the color coding gives you the different network providers. And you see we have a very nice distribution, and with Tahiti in the middle of the South Pacific, which was crucial to have a complete coverage. So what regards the redundancy approach here in this network, We have not put, say, normally not dedicated redundancy into the stations, with the exception of Tahiti, because there is no other station. For all the other stations, you have alternative ground stations which can be used to supplement if needed. If one station is out, then another one can step in. This is the high-level architecture of the the network and the processing center. On the top left, you see basically the ground stations and the station providers. In the middle part, you have the duplicated processing infrastructure which we put in place. So you have the relay part, which is basically file servers and handling the data exchange. In the middle, you have the processing servers, and the lower part is the archiving and storage facility which we have in place. The operations concept is asking for a fully automated system with automated error recovery in order to keep the cost of all this at bay. Of course, there is watchdog software which checks the proper functioning of the systems. An operations team is on standby and on call 365 days a year. So redundancy policy I have already explained. We have a fully redundant processing center and partially redundant network. The orbit products can be based on predictions of the orbits, since the achieved accuracies are sufficient then to satisfy our accuracy requirements. The clock products, obviously, clocks cannot be forecast. So this is a task which runs every 15 minutes and is taking basically 25 minutes of data and then determining the station and satellite clocks. This is the main monitoring screen of the network. On the left side, you focus on the stations itself. On the top right, it's monitoring the hardware and the communications. And below, this is the functions overview and the functions monitoring. This system has been now in operation since METOP launch, which was in October 2006. We achieve an availability of measured in these 4 years of 99.7%. We have service interruptions, which is maximum 1 per month for only a few minutes. The allowed criteria was below 3, so this is easily met. We meet consistently the required accuracies. And we have, in this July, we have updated the orbit prediction software to a newer package, which is giving even better quality orbits. And here, this is showing you for July the achieved GPS orbit accuracies. Each of these colors is reflecting one of the GPS satellites. I think there's 32 satellites in orbit, and not each month every satellite is declared fully functional. This is on the left, we have what is called a GSN metric, which is given the accuracy in centimeters, but on a 3 sigma statistic basis. And on the right, we display the IGS metric, which is on a 1 sigma and giving then it appears to be of higher quality because the numbers are smaller, but in fact it can be just easily be converted. On 18 July, which is where you see this downfall or the improvement in accuracies, we switched to the new software package, and it had an immediate effect here. By the way, the numbers on the x-axis are days from the going into operations of the GPS system. So it's somewhere in the 80s, the starting point for this counting here. So we achieve actually something like 5 centimeters accuracy now for the GPS satellites. This is a similar display for the clocks, and as this software package is not used or not having such an impact on the clock's estimation, there is basically a stable clock accuracy behavior in this month. And on the right-hand side, we have displayed here the RMS and standard deviation, with the RMS something like 0.3 nanosecond and the and 0.2 for the standard deviation. This now summarizes the impact that software change had on the accuracies that we derive for the position of the MEDOP satellite. And you see also here, you go down for the 3D component from something like 11 centimeters to something like 9 centimeters with the new package. Where are we going with this? There are some evolutions which we are planning to introduce. One is to reduce the timeliness, as we will introduce an Antarctic dump station in the next year or so. So we have to reduce also the delivery time for these GSN support products to something like below 45 minutes instead of 60. We want to play a bit with the configuration of the orbit predictions, as this can still be improved. We think about introducing a so-called navigation bit product service, which will allow to dive deeper in the atmosphere, because here you can then try, even when the receiver has lost lock on the GPS signal, you can try to get more information when you know the coding sequence of the GPS signal, and you can try to find this again in the still recorded, signal plus noise. Yeah, and we are going towards a real-time system in the end, because we have also a network which is getting direct readout data from the satellites, and which would require even lower timeliness. This is giving the acknowledgement to all the people involved here, which is the GSN team at ESOC, the GRAS team at EUMETSAT, the station providers, and Météo France. And this is, I thank you for the attention.
Questions?
Would the lower altitude occultation measurements allow you to bring the region that you can get accurate temperature measurements from the atmosphere down closer to sea level? Is that the intention there?
Yeah, very close to. I'm not quite to sea level, but I mean
below the boundary between
below
the
1 kilometer.
Yeah.
That's what we aim for. Yeah, we now get occasionally down to 1-2 kilometers, but that's an exception today. And then we will be consistently around and below 1 kilometer.
Right. Great.
Yeah.
Thank you.
And then we, of course, have also to change our processing, because then moisture becomes more prominent in the problem, and then you have to deal with this as well. Yeah. Yeah.
And then the upgrade or migration you made in June and to Nepils,
Yeah.
Is that a set of software that enabled better accuracy?
That's a state-of-the-art orbit prediction system, yeah.
So it has hardware as well as the...
No, it's software.
It's all software.
Yeah, yeah.
It's not like... So you gained more resolution because of the software. You didn't change the way that observation data was.
No.
Any more questions? Okay, let's move on. Thanks again.
Thank you.
I'm from the University of Washington. This is this is what I call my EScience Evangelist talk, or it's meant to raise some issues that we're having in astronomical data analysis, and hopefully articulate to the broader eScience community, the challenges that we're facing and what some of our needs are. And some of the work that I'll be talking about today is supported by NASA, the Advanced Information Science Research Program, and NSF. All right, so if we cast our minds back to the good old days, if you're an astronomer, you'll remember this. With the way that we used to do observing was we actually would go and observe. We'd go to a telescope, we would collect data, we would store that data on tape, and we'd take that data back with us, analyze it on a workstation, engage in the knowledge discovery process, and extract scientific knowledge from that and publish it. And so this was a paradigm that's still actively used today, of course. We still have telescopes that we go visit. But something that's come along and really changed the landscape is sky surveys. The biggest one so far is the Sloan Digital Sky Survey, was completed around 2005. And with this one, the data set became large enough that if you wanted to do problems that involved analyzing a large fraction of the data set, either reprocessing a large number of images or taking like all the galaxies in the Sloan Sky Survey or something like that, it exceeded the capacity of workstations. And so we were largely able to buy our way out of this problem and just by big beefy servers. And we are still capable of doing science. And so the first thing I want to say is, why is it critical to us that we have these serial resources? And the reason is that astronomers they actually write their own programs for the most part. Astronomers have been using computers ever since computers have been in existence, and they're used to writing their own code. And so it's obviously much easier to write code for a serial platform than it is for a scalable or parallel one. And the reason, generically the reason why this is true is because they do lots of math. The act of doing astronomy is you are comparing data to fairly sophisticated physical models. And so the models are complex. The data reduction process is fairly complicated these days. And the key point here is it's essentially the math that makes each researcher different from everyone else. So the key thing is that we all kind of have access to the same data now, right? Everyone using the Sloan Digital Sky Survey has access to the whole Sloan Digital Sky Survey. So the way that one astronomer is going to differentiate themselves from another is not because of the data set we have access to. It's because we're doing a slightly different analysis than anyone else. And so what this means in practice is that it's difficult to provide canned applications that serve the needs of a broad range of astronomers, because everyone's got to kind of get in there and tweak it and do their own thing. And so it's this reason why the domain has really evolved to everyone kind of writing their own stuff. Okay, so as long as we can do this in serial, I think we're doing pretty good. But the next generation of sky surveys, we won't be able to do that anymore. If we do a lot of investigations that use even a small-ish fraction of LSST, for example, will probably demand scalable resources, and this will be a challenge. we're going to have to use some sort of scalable system to analyze it. And the question is how then are astronomers going to be able to write scalable applications, and are they going to still be able, probably they're not going to be able to sit down and write code from scratch the way they do now and have the code be scalable because they just won't have the time. And the other question is, of course, what architectures will these actually be? And we've seen a lot of discussion on that. And one thing I want to emphasize is that we do know how to write parallel code in astronomy. I come from computational astrophysics, and we've been running on massively parallel platforms for 15 to 20 years. And so that set of expertise does exist in the domain. But what I want to emphasize is really what's different here is the human element. So when we write a simulation code, we invest a lot of time and a lot of effort into writing this, and it becomes scalable. The writing of the code is largely a technical exercise. What algorithm do we use? How can we achieve scalability? But once we write the code, we ship it off to the supercomputer, we run it in batch mode, and essentially it just becomes a data generator for us. But no science is actually done with the parallel code, right? Where the science actually occurs is when the human starts interacting with the data, and that we were fortunate enough in 1995 we could still do that on the workstation. So even though we knew how to write parallel code, we were writing the analysis code, on our one-off serial programs the way we've been used to doing. And so, so we were just as happy as the observers. And this started changing about 10 years ago when the machine started getting big enough. It's roughly 1,000 processors. At that stage in astrophysics, you hit the point where you start overloading the capacity of a workstation. And so, you can buy your way out of the problem for a little bit and just buy a beefy server. But a couple years later, we went through another order of magnitude gain in processing cores, and we could no longer analyze the simulation that the supercomputer could spit out. And so we did there's a saying that if at first you don't succeed, redefine success. So what we do is we just don't run on the biggest supercomputer. We use a smaller subset of cores, and that's the way we've gotten around on it. But supercomputers keep getting bigger, and in another year or two, we're going to have Blue Waters, the IBM machine at NCSA, which will have 300,000 cores, and a simulation which will run on that. If we dump the state of the system, which is 500 million particles or so, a single snapshot's going to be about 100 terabytes, and we can generate 1,000 of these if we wanted to, right? So we can basically fill up any storage device you can plug into the hardware. And so, what do we do then? Who knows? All right, so what the scalability challenge is not about. So first of all, it's not for lack of parallel programming expertise. We know how to write scalable programs. We just don't know how to write them quickly, right? And the other thing is what's becoming more common is for at least larger research groups to employ full-time software developers. So at least there's some potential that the code will be reusable. But we know how to write parallel programs. We also have amazing access to scalable resources right now. We already run on the largest supercomputers in the world. Every researcher has access to hundreds of millions of dollars of hardware, and these platforms are evolving to meet data-centric computing needs as well. There's a lot of interesting discussion about what's the right way for them to evolve and everything, but I think we can say that the evolution will occur, and we as researchers will have access to whatever the most appropriate architectures are. So I'm not really focusing on this, but what it really boils down to is economics, that at the moment, our current development time for parallel code is that it's very expensive. And in the simulation world, that's fine because the code is reused for decades and by many researchers. So even if you put 10 FTEs, into developing a code, that's fine, because economically you'll get a lot more science out of that. But data analysis doesn't work that way. And so what we want is this speed of scalable application development to proceed at the speed of science, and hopefully not as fast as my email client. So we'll do a survey here of the different ways of different tools that are available for developing scalable applications. And so if we start at the bottom, the least abstract, you have basic message passing, MPI. This is what most codes are written in these days. If you're lucky, there's a library that does what you want. But the problem is, if it doesn't do exactly what you want, then it can be challenging to use these things. One of the more interesting developments lately, I think, are what are called PGAS compilers or languages. They used to be called DSM languages, distributed shared memory. They're now called PGAS for Partition Global Address Space. And what this is it's a language that gives you a view of your data like it's just one big pile of data, and where you can address anything regardless of what node it physically is located on. And then they can be adapted to shared nothing storage architectures too. And it doesn't have to be just what RAM that data element is located in. And let's see, UPC and Titanium were actually developed here at Berkeley. And these are, I think the first three are about 10 years old now. These two, Chapel is being developed by Cray, and X10 is being developed by IBM. And they're brand new. We haven't really had a chance to play with them yet. And I'll talk a little bit more about those in a minute. Then moving further up the abstraction scale, we have data-intensive frameworks like MapReduce and Dryad. And then at the top, I would put relational databases. So, the key here being that sort of the more abstract you can get, the less time it's probably going to take you to develop whatever data analysis workflow you have. All right, so what we want to answer is which one of these developed models provides the scalability that I need, keeps the astronomer's development time on par to something that they're used to, and but retains enough flexibility for each astronomer to do the analysis methodology that uniquely defines them. And so if we look at databases, the sort of the point of databases is that they provide a very high level of abstraction. So if you can express your query, in a language they understand, then you're set. One thing that's been missing until recently, I think, which is why scientists had not used them, is user-defined functions. Because again, astronomers at least do a fair amount of mathematics. And so that's going to be sort of intrinsic to any query that they do. So the ability to sort of plug that math into the database and have it handle it was sort of I think one of the most critical aspects of flexibility. There's other enhancements that have occurred, and obviously, the last 5 years have been an era where DBMSs have really evolved to be more congruent with the needs of researchers in general. So we'll say that those two are good, but but it's scalability where the real challenge is. And this is a plot of just a test that we did about 1.5 years ago, where we compared. Bill, your name is not on here, and I'm sorry about that. Bill actually did the RDBMS. All right, fire whoever made the slide. The first query here, the green, was just a simple select. So we're selecting on quantity that's already in the database. And as you would expect, the relational database is very fast. The other thing I should point out is that the hardware on that we ran the the database and Hadoop is identical, so the y-axis here is actually meaningful. And so the database is fast, and you expect that. It also scales, and then Hadoop, because it doesn't have indexing, it has to read in all the data, is going to take longer, but it's scalable. The interesting thing is all we did is we just made the select a little bit more complicated. We essentially put in some math. We asked it to calculate the quantity we were selecting over based on the numbers in several of the columns of the data. So in other words, the database couldn't predict, it couldn't really index on this quantity because we were just sort of throwing it at the database. And it's still data parallel, though. And the database had a hard time with this. It didn't scale, whereas Hadoop did. So that's just a quick illustration. I mean, I think the bigger thing to take away from this is, so if you're in this situation, what do you do, right? Because the database is kind of a black box. And so we don't know why it scaled here. Maybe eventually we could have figured it out. But even if we could have figured it out, could we really have done anything, other than call up the vendor and ask them to please fix this in the next software release? So, all right, so that's databases. Frameworks. The good thing about frameworks is that they're designed from the ground up to be scalable. So obviously they provide high scalability, provided you can fit into the programming model. Different frameworks have different boxes that you have to fit into. MapReduce is fairly restrictive, although it is amazing what you can fit into MapReduce if you think about it long enough. Dryad is a lot less restrictive than MapReduce, for example. So that depends. The challenge is in the development time. When we started this one project that I'm showing you a slide of here in the hopes that we could actually give Hadoop to astronomers and just have astronomers write their own Hadoop functions, their Hadoop methods. And I think that turned out to just not be feasible because we found that you just had to know so much about the way Hadoop works before you could extract decent performance out of it, that you basically had to become a Hadoop developer in order to use it. And so it just didn't have the ease of use that we wanted. And what you're seeing here is this is sort of our most naive approach to dumping data into Hadoop and trying to extract. In this case, we're extracting images that overlap a particular region of the sky. So we're putting in like 100,000 images that cover a broad range of the sky, and all we're doing is we're saying we want a 1 square degree area of that. And so the naive approach where we just dump the images in takes a long time. If we do some very simple thing, which is all we did is we took the image files and we essentially put them into tar files. That's the Hadoop version of this is called a sequence file, but they're archived. So we just lowered the number of files. So it's the same amount of data. We just put them in fewer files. We get a factor of 4 to 5 speed up just by doing that. That's not an obvious thing that someone would think of, And then if we do further partitioning and stuff like that, we can get a little bit more performance out of. So I think our experience so far has been it's hard to imagine a scientist really using this as their main development platform. And then, and thirdly, PGAS languages are really interesting. So the main thing with them is they're trying to minimize development time. And so they do that pretty well because that's their primary design goal. And the challenge with them historically has been flexibility. You really have to be able to fit into their programming model before you can use them. And that's the reason they haven't really gained a lot of penetration, even in the HPC community, with who they were designed for. But they're becoming more flexible all the time. Chapel and X10 are specifically designed to sort of conquer the flexibility barrier. And then scalability, again, if you can flex yourself into their programming model, they're going to be fairly scalable. I just put these in questions because we haven't been able to evaluate the latest generation of PGAS languages. But one thing I will say, so if you look at MapReduce, for example, it's an example of bulk synchronous parallelism, which is you do a lot of local computation, data parallel computation. Then there's there's a collective communication phase where all the nodes send stuff to everyone else, and there's a barrier, and then you sort of repeat. I guess in MapReduce there'd be a reduce phase and then another barrier. But it's essentially a bulk synchronous framework. And so if you look at this programmatically, like forget about what architecture I'm running this on at the moment and just say, well, as a programmer, which would I prefer to use? I would make the argument that a PGAS language is almost always going to be easier than Hadoop. Now, you can also say, well, Hadoop's geared towards a specific architecture, which a PGAS language isn't, and vice versa. And there's a lot of interesting discussion we can have there. But anyway, I just want to sort of put this as a plug for the PGAS languages. I think they are geared to being very easy to use. So just a summary slide. For astronomy, data-intensive scalable computing is an attempt to have 3 oppositional properties at the same time. Flexibility is the key issue here. We have to be able to flex to every astronomer's needs. But we also need the scalability to handle the data sets, and we need to do it in a short development time. All of the things I talked about today, none of them really quite do it, but the 3 main ones I think are all promising candidates. They just kind of have to go a little bit further. So PGAS languages are very easy to use. Their Achilles heel is flexibility, but the latest ones are working on that. For the frameworks, I think where we really want to put our investigative effort is into are the languages and interfaces that are being built on top of these, like Pig and Hive for Hadoop, and then Dryad Link for Dryad. We really want to investigate, because you get a higher level abstraction with these, and what we want to make sure is that you don't get rid of the flexibility that you need. And then databases are, of course, being pushed to larger scales and tuned to the needs of science. I think with these, what's going to be hard is achieving the scalability, but also still offering UDFs in a scalable manner. It's going to be challenging for a database to be able to scale these, what to it are black box user-defined functions that users are writing. That's it. Thanks.
Thank you, Jeffrey. Any questions?
In regards to the PGAS languages, how many actual working implementations are there of any of those languages?
There are working implementations of Coré, Fortran, and UPC. And there are prototypes, working prototypes of X10 and Chapel, to my knowledge, but I have not tried them. But if you ask IBM, they will happily let you run X10. I just haven't gone through that exercise.
Are you optimistic about SciDB?
I really know virtually nothing about SciDB other than they seem to be doing cool stuff, but I haven't taken a close look at it. I really hope that it's something really useful. I want to be optimistic about it because we've had a lot of success in astronomy using DBMSs. They become way more common than they were 5 or 10 years ago, and there's a lot of good success stories there. And I wish that we could just keep going with that.
So there's one slide that you mentioned that the lack of user-defined functions.
Mm-hmm.
You mean that SQL query language lack of? I didn't quite get it. What is the system that you were trying to develop not providing enough user-defined functions, or?
Well, if you go back 10 years ago, to put your own function into a database was there was a lot of overhead when you ran that function. So the function is written in a language at SQL, it's like C# or something. And you have depending on the database, you have your choice of languages that it will understand, that you can write a function in. So you don't write the function in SQL. You write the function in a more procedural language.
And then you attach that.
Right, and then you sort of plug that in. So it's, for scientifically, it's a way of encapsulating the math that you're used to doing. And people build libraries of these UDFs. There's a cosmology, a UDF library for SQL Server right now, for example. So it makes it a lot easier for astronomers to use SQL Server for their purposes because they have these pre-written libraries they can leverage. So my contention was you need to have these things for databases to be useful.
So,
That makes
Bill,
sense?
what is your think of that?
I think the point is that optimization in the presence of UDFs is a harder problem than optimization in lack of UDFs. And that
Yeah.
despite what the vendor brochures say, when you're actually going to try to prove based on all your work on tons of UDFs, your performance.
Right. Oh, okay. From that perspective, fair. Yeah.
Right, yeah. And then my point at the end was I
Right.
think the challenge
Yeah.
to scalability is definitely going to be.
It's not so much you can't, they don't support UDFs, they do. But
They do
Yeah,
now,
they
yeah,
do
yeah.
have that procedures that you can associate with all that. Okay, I got it. Yeah.
Okay.
Great. With that, we close this session. Thanks again.